Hello and welcome to EP2P04. This is going to be practice for topic number 5, and today we're going to do the 2019 test number 5, which is pretty representative of what we're going for this year as well. Okay, so consider the following system showing frame ABCDE and its adjacent connections, where W, the distributed load, W at X applied to the top here, is given by this function that is kind of sinusoidal with an offset so that it's always a positive number and W is directed down. Okay, and coordinates of the points are in meters given here. The force at F is applied, that's up there, is applied with an angle of 30 degrees above the horizontal. Draw an FBD for this frame, solve for the reaction forces and moments acting on the frame, and draw an internal shear force, normal force, and bending moment diagram for the frame. Okay, so that's what we're going for here. So the first step is to draw a free body diagram for this whole object and solve for the reactions at B and the tension in this cable E. There's a cable there applied. That's what this thing is. Then once we've got those, we'll be able to solve for also the reaction forces here at C. Actually, I guess we could do this in a couple of different orders. We could look at the whole body and then find those things, or we could first look at CF as its own thing and then figure out what must be going on at C. Let's use that as a check. Okay, so first we'll take the entire thing and let's do the same thing that we did last time to let us split this up. Yeah, so we'll take that there, and now we'll put a new layer in, and then we'll copy this whole thing and paste that down there. Whoops, I was selecting the wrong layer. Okay, here we go. There's a way to view the layers. There it is, this thing. And now we say I'm going to select the background, copy, and then in layer 2 paste, and now we've got something in layer 2 specifically. Okay, so it's this whole shape there, and then what I want to do is draw the external reaction forces that are on this thing. So we've got Bx there, and we've got the reaction force in Y. Let's call that this thing. By, and we've got a tension here at E. So let's call this the tension. Sure, why not? So there's our free body diagram for this whole thing. It'd be good to show what the points are in this diagram as well, what the X and Y coordinates are for these different parts of the beam, just to make sure we're absolutely clear on on where stuff is located. They are giving us a width of the beam, so we may have to account for the fact that this is displaced up a little bit compared to the center. So let's put in some coordinates. Maybe we'll go to a smaller font size here. Yeah, so A is at 0, 0, and we'll make this non-italic. Okay, B is at location 1, 0. So this is 1 over to the right. Then C is at location 2 and 0.3. D is at location 4, 0. E is at location 4.3. 4 and 0.3, that is, 0.3 up. And F is at location 2 and 2.3. Okay, so should now be in a position to copy that thing and paste it in. So first thing, free body diagram, done. Next step is going to be to apply Newton's second law to this thing and get and find out what B, X, and By and the tension are. Okay, so we'll restart this. We'll put in what the distributed load is, which was given in the problem. W is equal to 300 times 1 minus 0.5 times sine of 2 times pi times x over 4. There is our distributed load typed out. And we can plot that. 0 to, looks like 4 is going to be all the way across this. That's the x displacement from the left side to the right side. All right. We can also set y equals 0 to 450. Yeah, there we go. So its some distributed load looks kind of, I guess, vaguely like what we've drawn there. Sort of a sinusoid, down, up, and then down with an offset. It's always positive. So the next step is the Newton's second law applied on different parts of these. So we'll say solve net force in x is 0, which would be bx plus, let's put in the angle for that thing up at the top. So let's call that Q is 30 degrees. So bx plus 400 times cos of Q. In the y direction, by plus 400 times sine of Q plus t. And the net, also the integral of w minus integral of w from x is equal to 0 to 4 over the whole thing. And the torque, we can take the torque about any point. Why don't we take the torque about point B? Sure. Okay, so torque about B will have the force W creating a torque by the distance that we are to the right of this times dx times w. So distance we are to the right of it would be x minus 1, that's the location of B. Dx, meaning we're going to integrate, times w. Over the whole thing. So let's see, what is this do we have to check the right hand rule? Right, we have to see if this is doing the torque in the right direction. Normally we want the torque to be added out of the page for positive, and this would be creating a torque into the page, rotating the other way in the clockwise direction. So we actually want to multiply that distance by negative w. Okay, so that'll be the torque produced by the distributed load. The other ones are not so bad. We're going to have a torque from the tension, which is 4, which is at location 4, so 4 minus 1 is the moment arm, times the tension, and that is in the positive direction, moving up that way. Now, at point F, we would have, we have a couple of different ways that we could calculate this. We could try putting in like a total cross product type thing, but to stick with the one-dimensional version of it where we're just summing it in Z directly, it's probably best to think about the x and y components of this. So we go, we would have the x displacement times the y part of the force. X displacement would be 2 minus 1, so the x coordinate 2 minus x coordinate 1 times the y part of the force, which is 400 sine of Q, and that creates a positive torque about B. And the x part of the force would create a negative torque, a torque in negative Z about point B, and that would be based on the y displacement, which is, oh no, there we go. Yeah, 2.3. That's how far it is up, right? We did that. The number's looking kind of strange. Is this right? Point F is at 2.3 up? Okay, good. So that will be 2.3 minus the 0 height that point B was at times the x component of that force, which is 400 times cos of Q. Okay. So if we haven't made any mistakes there, then we should be able to solve for B, X, By, and the tension. It looks like the tension is positive. That's good, because otherwise this would fall down, and that could be because of the force there and the distributed load pushing more on this side of it than the other one. Bx has to be negative, and that makes sense because the only other x force on here is from the component of this force here applied at the top, so we have to have Bx counteracting that. And then By ends up being positive because the weight of the W distributed load is mostly in the downward direction, and even applying this tension up is not enough to counteract the force of this. So you could see that by taking the torque about point E, the tension will not be able to contribute W is mostly going down and I guess overpowering what this force is doing at F. So By has to be positive to counteract that. Okay. All right, so let's copy this in. And we don't really need to have a look at the weight force there. So let's get rid of that and just put in the raw solving that we had as the solution to this. So we apply Newton's second law to this and find that out. Okay, now what we're going to do is do a free body diagram for just CF, splitting that apart and seeing what the internal force is there for us to be able to draw a shear force and bending moment diagram for ABCDE. To do this, we'll take this segment of it and kind of cut this and paste it up a bit. Wonder if that's the right way to do this. Maybe it would be better to do a more precise selection that just gets at this thing. Yeah, and leaves as much of the distributed load there as possible. Okay, so we'll cut that and paste this thing just up there. And then maybe copy in the coordinate C to point out that we're still talking about the same point there. Okay, cool. Now we're in a position to draw in the forces applied to this. So you can look at this thing and think what has to be applied at the bottom. We've got to have a force. I mean, you could just jump right in and say, well, for sure, we're going to have force the same as the forces F at a down and 30-degree angle there. But let's pretend we don't know that. Let's just do the standard way and call this CX. And another one like that, which is CY. CY, labeling them both at once there. And we're going to have another CX here as a Newton's third law action-reaction pair applied to the bottom like that. Okay, but that's not it. Because it's a fixed support, you could tell already by the C force that would have to be there to counteract this. We also are going to need a moment applied to this to counter that. And you can tell what way that has to be by the one that would counteract the couple produced by this force and that force. That's going to tend to make it spin like this. So we need a moment applied in the other direction. Again, it's okay if you don't apply this in the right direction at the start, because then you'll just get a negative answer for it, but the rest of the math will work out fine. It's no problem. So it doesn't matter at all that in this last part of the solution, for example, Bx ended up being negative. No worries. We're going to not worry about that and still assign everything as if Bx points to the right. The fact that it's negative something to the right doesn't affect us at all. Okay, so there's MC. Not sure if this label's close enough to apply to that. Let's write it again just in case. MC there. Yeah, okay. So there we go. There's our new free body diagram to figure out what's going on at this connection, the junction at point C. So now we can do Newton's second law on this piece as well. So let's do, it doesn't actually depend on this first stuff, but let's just go ahead and put this in by looking at this top piece and see if we can solve for MC, CY, and CX. And then we'll do it for the whole piece to see if we can get a bit of a check going on there. Okay, so what we would have then is on this top piece, on just CF, solve minus CX plus 400 cos of 30 minus CY plus 400 sine of 30. And for the moment, we would have, let's find the torque about the bottom. So we'd have plus MC minus 400 cos of Q times 2. 2 is the height difference. Maybe let's make that 2.3 minus 0.3 to make it more clear where that came from. That much up, and then just the x component, because there's no x displacement, so we don't have any part of the y component contributing to the force about this point. Yeah, so there's that. And then anything else? No, because we found the torque about the bottom. That should be it. All right. So that lets us find what MC, CX, and CY are. Now, just as a check, we can go and find out whether or not this beam is in equilibrium if we use Cx, Mc, and Cy instead of the components of F that we included the first time. So let's assign this. And then let's just write out the equations. We'll assign the previous one as well. And then we'll return to these equations. So let's execute that to assign those. Now let's just have these equations and see what they each say. So we're not going to apply this. The now x component is that plus Cx. And y component would be this plus Cy. And then here we'll have not this stuff, but torque about B, we would have, let's see, we'd have this. Unfortunately, both of these components do create a torque about B because it's displaced in both x and y. So we'd have 2 minus 1, that's the x displacement, times the y force. Instead of this, we'll have Cy. And not 2.3 minus 1, but only minus 0, but only 0.3 minus 0 times the x component. And then we also will have to add in MC. But on this, on ABCDE, it goes in the opposite direction. So we'll be subtracting that. Okay, so let's see what this says. Ooh, we have something that didn't add up to 0. So something is amiss here. Aha. So looking through the way we added these all, one of the torque components is wrong. Can you see which one? So this one here, the Cx, actually we're at a displacement of 2 up. This creates a torque in the negative direction, so we should have subtracted that instead of adding it. Now it's worse. Aha! The problem is that actually we made that same mistake in the first one. So this one, when we were calculating the contribution that the x component had to this force, we should have subtracted that as well. Right. And now that changes up what these, what the tension and By should have been. So that explains why By was so large earlier compared to what was going on with the tension for these other forces. And now we do indeed get a check that has worked out. So do checks. It's very easy. Even when you've been doing this for, I don't know how long, maybe like 1,000 years I've been doing these kind of questions. You can still make mistakes. So it's worth doing a check. Okay, so I've gone and updated the new check, pointing out that we updated this one as well, fixed that that mistake that was in there originally, and then applied the equilibrium of CF, explained that that's what we were doing in this code by adding in this extra solve line there, and incorporated the check as well to show how that works. Now we're in a position where we can start finding the internal force and moment. The first step is to draw a free body diagram that we're going to use for that, and we can again take something like this and split it up and then just draw in what's going on this internal stuff. So let's label a split there. We've got our force N, normal force. We've got our shear force down on that side, up on that side by default, V, using the sign convention that we're sticking with, and the moment, internal bending moment. There we go, and there it is, M and M. Okay, so with this in mind, we can now write down what's going to be going on for building up the shear force, the normal force, and the bending moment. And the way to do that is to start defining them. So let's see, again using Newton's second law. So let's start off with the normal force. Normal force is going to be 0 until we pass point B. piecewise, if x is greater than the coordinates of b1, then we're going to have to subtract bx. Then it's not going to change till we pass point C. Piecewise, x is greater than 2, which is the coordinates of point C, in which case we are going to be subtracting off cx, right? Because bx is going to be applied to the left of this. So if you like, you can imagine when we split it over here. Whoops. To zoom. Maybe I should have zoomed out a bit before doing that, so it's a little bit less crazy. Okay, so on this side, we're going to have the... Actually, maybe I can just copy this. Ooh, that's pretty good. Yeah, we're going to have the same shear force, bending moment, and normal force directions, but we're going to be applying them over on this part as well. So you can see as we pass bx and then cx, the normal force is going to have to reduce because we have more forces added to the right on this object. Now, in fact, bx is negative, so the normal force will actually increase by negative bx as we cross point B, but still we write down our piecewise function as this, as a minus bx as you cross that point, and that'll take care of it. Okay, so that's the normal force. We can plot it immediately just to check that it's working. Yeah, so increases up to 350. It only applies in between B and C, and otherwise the normal force is just 0. Next up, shear force. So let's see. When do we have shear force added? V is going to be increasing by is going to be adding up the total W that's happened so far and have to oppose that. So that means that we're going to take first the integral of W from x is 0 to x up to the point that we're at, but we're going to have to oppose that. So the integral of negative W from x is 0 up to x. Then we're going to add in a piecewise function, piecewise of that accounts for all of the point forces that we have. So V is going to increase by by after we cross x is 1. So if x is greater than 1, by. Then a piecewise increase again after we cross point C by cy. And just to close it out and make sure that it goes back to 0, after we cross point E by the tension. Okay, let's plot that as well. Yeah, so starts off at 0, and then it's becoming negative, but has a big jump when it counteracts by, then curving again, but by a different slope as we're moving across here, and jumps again after we cross cy, then curving down, and the tension will have to be quite large. Let's take this plot slightly further than 4.1. Yeah, jumps back up to 0. Now we didn't tell us that the distributed load stops, so it's still going to plot that a little bit more. Let's go to 4.01 to make it go just slightly past and then stop there. Okay, great. And the final part is the internal bending moment, which is easiest to get by integrating the shear force from x is 0 to x, and then just adding in any piecewise, any point moments that are applied. In this case, only at point C. Plus piecewise, x is greater than 2, mc. Yeah, you can see that that will be adding to this one because this is trying to spin it in the opposite direction to what our m is, what our internal moment is directed to do here. Okay, so let's see if that works. Okay, so there's the internal moment. It right away we have an issue. It does not go to 0 at the end. So there's some concern with this, right? Now what's up with that? Well, actually there was one other thing that's creating a point moment as we go across this, and that's this force Cx applied here. So the derivation that we were getting that was saying that the moment is the integral of the shear force, that assumes that we didn't have any kind of point moments applied from like an x force there. This basically creates an extra moment from the 0.3 up from the center line displacement that it's at. So that means that we need to add that in as well, not just mc, but plus cx times 0.3. That, like mc, is going to create a moment that spins this in the clockwise direction. So we have to add that as well to get the moment graph to line up. And there it is. Thanks for watching. I'll see you next time.